my name is Sophie Hudson, and my talk today is called Swift WTF. I'm here in Japan for 2 weeks, and I want to visit all your stationery shops, all your anime shops, and all your video game arcades. But right now, I want to talk about Swift. I was only 4 years old when Swift was announced back in 2014, but I know that lots of experienced developers were very happy to see an all-new programming language, one that was built from the ground up to be modern and avoid some of the weird behaviors that other languages have. Sometimes people think Swift is perfect, that the code they write is always going to make sense because Swift is so much better than other languages. But for me, Swift developers who look down on JavaScript developers sound just the same as World of Warcraft players who look down on the Sims players. So my talk today is called Swift WTF. And as you'll know, WTF stands for Weirdness, Traps, and Fixes. I want to show you some things that I found confusing when I was learning Swift. In each case, Swift is doing exactly the right thing. It's behaving exactly as it's supposed to. But it still surprised me, and perhaps it will surprise you too. We'll start with the easiest stuff and work our way up. It's a bit like climbing increasingly steep mountains. There are some gentle green hills anyone can climb up, and there are some big mountains that are much more challenging. We're going to start here, on this little green hill. This first thing surprised me, but I think smart people like you will already know about it. Let's say we saw two numbers, one with the value 0.1 and another with the value 0.2. If we add the first number to itself, that'll make 0.2, right? Right. And if you add the second number to itself, that'll make 0.4. But if you add the first number to the second number, it won't make 0.3. This code will print false. What the heck is happening? This happens because the actual sum of 0.1 plus 0.2 is this. 0.3 with a whole lot of zeros that are 4 at the end. It's not like Swift can't store 0.3 in a value, because it can. This will seem to work just fine. Despite it looking wrong, Swift is doing exactly the right thing here. This is the intended behavior. This behavior is formally defined as IEEE 754, which I'll be honest with you, is something I've never read. But it means that all other languages do exactly the same thing. All these and more would say that 0.1 plus 0.2 is not exactly 0.3. You'll already know that in binary integers, as we move numbers to the left, they get bigger. So this is the number 1. One place to the left would be number 2. This would be the number 4, and that would be the number 8. But let's think about how that works in numbers below 1. This would represent 1, just like before. But now every time we move one place to the right, we don't double our number, we're halving it. So this would be 0.5. If we go another place to the right, we halve it again, making 0.25. Another place to the right, 0.125. Then finally, a fourth place to the right, we would get 0.065, and so on. So we can represent a handful of numbers. I need to use those to make up all other numbers. So let's say we want to make 0.875. Initially, our number would be all zeros. We would start with 0.5, adding that to our number. It's now 0.5. We would then add 0.25 to our number, so it's now 0.75. And finally, we'd add 0.125 to reach our target number. But what about all other numbers? Every number that can't be reached through inverse powers of 2, which is most of them, can't be exactly represented. Even if we had a fairly long string of binary numbers, that still wouldn't exactly make 0.1. There's a tiny error. good enough that we're happy most of the time. Here's our Swift code from earlier. But remember, this time, none of these numbers can actually be stored in binary. So really, these are all approximately equal. First is approximately 0.1, second is approximately 0.2, and so on. The reason these two are true is because the errors are the same. The gap between the actual value and the closest binary representation matches. But this one fails, because the sum, including the tiny errors from earlier, is this number, 3, many zeros, then 4. Whereas if you assign directly, Swift can get a tiny bit closer. So now we have two different numbers, and the comparison fails. Anyway, this talk isn't just a maths lecture. I also want to show you ways to do better. If you're feeling fancy, Apple has a special library called Swift Numerics that handles approximate equality for you. But the much easier solution is to use a decimal type. This stores precise floating point numbers. So if your number is very important, you work at a bank, for example, this is the right approach. OK, that was easy, right? But that's one problem solved. Let's go up to a steeper mountain and try climbing that. Here is the very first Swift extension I ever wrote. Yes, I know it's simple, and I know it's not any easier than the original code, but I was learning, OK? And it works exactly as expected. 1 squared, 1. 10 squared is 100. 100 squared is 10,000, and so on. But then I tried this, negative 10 squared. Now, if you remember back to school, a negative number multiplied by another negative number makes a positive number. So I expected this to be 100, but it was not. Instead, minus 10 squared made minus 100. What is happening now? Remember, Swift is doing exactly the right thing. This is correct behavior. To understand the problem, consider this. What is 5 plus 5 times 5? You'll know that we consider multiplication to be a higher priority than addition. So we perform multiplication first, as so. And then we're left with 5 plus 25, making 30. Now, take a look at my code again. We can hide the print part, because it's not important. My mistake was that I thought the code meant this. Take the number minus 10 and multiply it by itself. That would have produced 100, because even in Swift 6, a negative number multiplied by another negative number makes a positive number. But here's how Swift sees it. If I insert some parentheses, it should become clearer. Swift squares the number first, then applies a negative sign. So 10 times 10 makes 100. Then making that negative will produce minus 100. And so the fix here is to make it clear what you mean. This kind of code is likely to trip you up. Instead, I now place parentheses into my code to make it explicit what I mean. These two create two different results, but at least I now get exactly what I want. OK. That was still pretty easy, right? But it's another problem solved. Let's go up to our third mountain. It's getting a bit steep now. If I make a string, then take a copy of it, my copy will also be a string. If I make an optional string, then take a copy of it, my copy will also be an optional string. But what happens if I use an implicitly unwrapped optional? What type will my copy have now? Well, it's obviously not a string. But neither is it an implicitly unwrapped optional string. Instead, it's a regular optional string. Now, I've always found optionals a little bit slippery in Swift, but this behavior is odd. Why is Swift doing this to me? What's happening here is that both of these have the same underlying type of data. They are both optional strings. The difference is that this one has an internal flag saying it's implicitly unwrapped, and that flag gets lost when copied. There are two ways to fix this. The first is to say that your copy is also an implicitly unwrapped optional. But the second is to ask yourself a very important question. Why are you still using these things in the first place? That wasn't easy, but neither was it something I would call hard either. So, let's go up to our fourth mountain. This one looks dangerous. You'll know that Swift lets us compare the content of arrays. So this will print true, because the numbers aren't the same. But did you know you can also use less than and greater than here? This will print true, because all the numbers on the left come before their counterparts on the right. If this is news to you, I'll give you a hint of why it's surprising behavior. This code won't work. It'll throw up an error. If you're still not sure, here's a second hint. Try deleting import foundation. With that change, the first line is still valid. The second one stops working, and the third one starts working. If you're still not sure, we can break it down even further. We know this line works when we include foundation. If we run the same thing twice, of course both will work correctly. But what if the second time we created our two sets of numbers as constants, and then used those constants for the comparison? Well, this one works and this one doesn't. Just making the values separate constants breaks the code. What in Federico's name is going on here? If we break it down, we can see this creates two arrays. Then checks if one is less than the other. But that's not allowed. Arrays aren't comparable in Swift. So why does this work, and only when foundation is available? Because these aren't arrays. These are both index paths, which are a bit like integer arrays, people older than 25. I've literally never used them in my entire life, so this behavior really confused me. It's also why the foundation import is required. Swift can create index paths from array syntax. Because we make them directly next to the less than operator, Swift treats them as only type that's valid, index paths. And that's why this code is allowed. Enough waffle. How can we fix this? You can use the brilliantly named lexicographically precedes method, which is basically a fancy way of saying comes before. Or you can make arrays comparable when they contain comparable objects. But that's above my pay grade, so I'll leave that as an exercise for you. So, now you've climbed all 4 of our mountains. You're all very smart people. So I think these have been quite easy for you compared to me. But what comes after that 4th mountain? Well, I do have one more thing. Let's say we have a string with the flags of 2 countries, Canada and the United States. If I asked you, does that string contain Canada? The answer is easy. Yes. Does it contain the United States? Still yes. How about Australia? Is that in there? Well, no. This is great, right? Swift is so easy. So how about if we replace all instances of Australia with Nicaragua, then print the result, what will be printed? Canada and US, right? Well, no. And you're not going to like the result, so brace yourselves. This might hurt. What's actually printed is China, Iceland. And this one, honestly, I don't think just saying WTF fully captures how much this almost broke my brain. When I was shown this code for the first time, I wanted to do horrible things to my computer and take up woodworking instead. But again, my code is working exactly as intended. This isn't a bug. Emoji are complex characters. These flags are stored as multiple letters internally, which then combine to make the flags. They always have 2 of these characters. For Canada, that's the country symbols C and A. And for the United States, that's the country symbols U and S. These special symbols must always come in pairs, never 1 or 3, but always exactly 2. So when Swift sees this U, it knows it must be followed by something else. And then as soon as it sees this S, it puts the 2 together to make the US flag. It does this automatically, which I think is really cool. But, and this is a very big but, we aren't only using Swift here. You see, if you go down below the Swift code we're using, all too often we find something else, something dark, something evil. Just kidding, it's Objective-C. Let's look at our code again. I've already said that Swift sees the symbols C and A together and recognizes that it makes a Canadian flag. It does the same for the symbols U and S, making the United States flag. But this method comes from Foundation, meaning it's Objective-C code. And Objective-C doesn't care about emoji. So when we say to replace Australia with Nicaragua, Objective-C looks at the text and finds the country code for Australia right there in the middle, AU. This totally breaks the rules of flag emoji. They must always come in pairs. So a C by itself at the start and an S at the end aren't valid. But like I said, Objective-C really doesn't care. It has found Australia and it's going to replace it with Nicaragua. So the AU in the middle becomes NI, which is the 2-letter code for Nicaragua. And now we have CNIS, which are the country codes for China, Iceland, which is why our flags change. So how can we fix this? Easy. Burn it all to the ground! But on a more serious note, rather than using old code like this, you want to switch to a Swift native version like this. It's less code, faster code, and safer code too. Swift native code like this will always treat emoji correctly as one single unit, rather than something that can be divided by accident. So now we've climbed our last and highest mountain, which means this talk is almost over. I hope I've helped you understand some of the things that I found weird when I was learning Swift. But now, I want you to help me. Like I said at the beginning, I'm here in Japan for 2 weeks, and I want to visit all your stationery shops, all your anime shops, and all your video game arcades. But I'm only 15, so I don't have any money, which I'm going to go home sad and out any awesome stationery. So, my dad made a deal with me. He said, for every person who takes a picture of me during this talk and uses it to tag him on any social network, he'll give me 200 yen. God, get those phones out, get ready. There are so many of you here. If you all posted a picture, I would earn enough to buy all the anime figures I ever wanted. So please tag me as Pink Straws on Twitter, Blue Sky, Threads, and Mastodon.social. All you've got to do is take a picture of me, here on stage, post it and tag me. I'll even pose for you. Come on, get those phones out, all of you over there. Come on, I need that money, please. Don't get them anime figurines, huh? Enough of that. I need to wrap up now. I hope that you can see the next time your code isn't behaving the way you expect. Just remember that lots of code has a little bit of weirdness if you look closely enough. The key is to know where the traps are, and also what fixes to use to solve the problems. If you do all that, you'll be fine. Thank you.